Hello everyone. In this video, I am going to talk about section 5.5 free body diagrams, 5.6 equations of equilibrium, and also section 5.7 constraints in statical determinacy. So typically in this video, in this PowerPoint, we're going to look at some 3D problems. A few examples here shows different supports that you're going to get. This is a general rule, as we talked about before. If the support prevents translation of a body, then there will be a reaction force. If rotation is prevented, then the couple moment it will be on your support reaction. So single bearing or hinge can prevent rotation by providing a resistive couple moment. However, it's usually preferred to use two or more properly aligned bearings or hinges in these cases. So only force reactions are generated and no moment reaction are created. You can always refer back to this diagrams whenever you're looking at the problem. Hey, what type of reaction support are we looking at here? Um, we talk about if a rigid body is in equilibrium, that means the net force equal to zero plus the net moment equal to zero. So for 3D problems, you're going to have six scalar equations of equilibrium. Sigma fx equal to zero, sigma fy equal to zero, sigma fz equal to zero. Also, you'll have three equations for moment. Sigma moment x equal to zero, sigma moment y equal to zero, sigma moment z equal to zero. We're going to look at some examples in a little bit. So the moment equations here can be determined about any point. Usually we choose the point with the maximum number of unknown forces represented to simplify the solution. We talk about why do we pick the maximum number of unknowns, because any forces passed through the point where moments are taken do not appear in the moment equation because they have zero moment arm in this case. There will sometimes be redundant constraints. That's under the condition when the body has more supports than necessary to hold the equilibrium. This becomes statically indeterminate. A problem that is statically indeterminate that has more unknowns than equations of equilibrium. Sometimes over here we have six unknowns. Yes, we do have six unknowns. However, there is nothing restricting the rotational motion about axis AB. So in some cases, there may be as many unknown reactions as there are equations of equilibrium. However, if the supports are not properly constrained, the body may become unstable for some loading cases. Example number one, we have support by thrust bearing at A and cable BC, and we have also this external force 80 pound. When we draw the free body diagram, we're going to show the supporting force FBC, external force F 80 pound, and also we have reaction force AX, AZ, and there's moment MAX and moment MAZ. We write our scalar equation. Since there's no force along the x direction, we can simply conclude that AX equal to zero. Okay, AXD is the only force along the x direction. Now, on the z direction, along the z direction, we have AZ, we have the 80 pound coming down, and we also have that FBC. So there's my equation for FZ. And we're going to do our moment about y-axis. Okay, so about y-axis, the only two forces are generating moment will be this 80 pound times the distance, which will be 1.5 feet. And then there's also the FBC. The moment arm will be 1.5 plus 1.5 feet together 3 feet. So that's my moment equation about y-axis. Solving the last two equations here, we got FBC and your AC as well. Keep going. We can write our moment about x-axis. Okay, again, about the x-axis over here, you have your MAX, and then that 40 pound FBC generating moment, and that moment arm is 6 feet, this part right here. And then that 80 pound, 80 pound is also generating moment that is 6 feet as well. This equation help us solve for the max, and then we can do our moment about point z. It looks like moment about point z will be 0. So therefore, conclusion is maz equal to 0. That a both 80 pounds and the FBC 40 pound, yes, they're generating moment, but about z axis, they're not generating a moment because they are parallel to the z axis. Okay, they both are vertical themselves, so they are not generating any moment about z axis. Next example, we have this a plate holding by three of them, three cables, okay? And then there's that 200 pound, external force. The weight of the plate itself is 500 pound. First, let's take a look at the free body diagram. All of the forces are vertical. You have your TA, TB, TC, and then the weight in the middle, 500 pounds, and then the external force, 200 pounds. We can write our equation. So, we can write our equation over here that sigma fz equal to 0. And the reason that we don't have sigma fx and the sigma fy is that we don't have any forces along the x direction. We also don't have any forces along the y direction either. So the only force equation we can put together is all the forces, and they are all on the z direction, positive going up, negative coming down. Next, we're going to do the sum of moment about the x-axis. Okay, so TB go through x-axis. TB is on the x-axis. Okay, so that means everything else is generating moment but TB. Okay, so you have TA generating moment, TC, and then 500, and then the 200. Be careful with the directions. Some of them clockwise, some of them counterclockwise, and be careful with the moment arm as well. Next thing, we're going to generate the writing moment about y-axis. Y-axis, you see, notice that TA is on the TA is on the y-axis. So in this case, TA is not generating any moment about y-axis, but everything else is. So this is everything else. You have your TB, your TC, and 500 and 200. Be careful with the moment arm and which direction is rotating. So there we have our three equations with our three unknowns, TA, TB, and TC. We're solving them. Um, Overall, whenever the result come out, if it's a positive, if the result's positive, that means it's the same direction as what you originally assumed in the free body diagram, and all of them come out to be positive going up. And then it means that what we assume in the free body diagram is correct. All of the TA, TB, TC, they're positive. They all are going up, pulling the plate. Next example. So over here, we're going to first draw our free body diagram. And at point A, you have support AX and AZ. Okay. Along the Z direction, there's no force because it's free to slide along the Y direction. Free to slide along the Y direction. That's why there's no AY. So you have your force, the blue one, coming out with a 30-60 degree angle. And I know it takes a little while to adjust to the 3D view. B, same thing. You have your by and your bz, but there's no bx because along the x direction, it's free to roll. C, similarly, you have cx and cy, but there's no cz because along the z direction, there's no constraint. It's free to roll on that z direction. So overall, that's first break down our force F into the X, Fx, and Fy, and then Fz as well, right? So we're going to use that 30-60 degree angle to help us break that blue force into the three different directions. Okay, since we know the magnitude is 80, we know the direction, we break our force Fa, X, Fy, and Fz. And then keep going. We're going to do sigma summation of all the forces along the x direction, summation of all the forces along the y direction. There's also summation of all the forces along the z direction. And then keep going. Summation of moment, mx, summation of moment along the y-axis, my, summation of moment of about z direction, mz. So all these together, we have all our unknowns, ax, az, by, bz, and cx, cy. 6 equations with 6 unknowns. This is all I want to show you in this section. Thank you for watching the video.